started recording. So, hello YouTube. This is day 3 of ray tracing in a weekend. A weekend is actually gone, and it's Monday, so we kind of failed in that sense. I will say in my defense, though, that because of streaming schedule, I always start streaming at 6 p.m. my time, more or less. And if I had to do this, entirely on my own on a weekend, I would start probably earlier than that. So that would have allowed me to get more time. In any case, yesterday we got very far. We got all the way up to positionable camera, not included. So we got to model different materials, glass, including glassy stuff, which introduces the concept of refracting instead of reflecting, and yeah, that is nice. So it's now time to do the positional camera stuff, and apparently, we're really close, so it's not going to take long. This is going to be probably a short stream because we were doing the positionable camera, defocus blur, and then this is where the book ends. So, but I didn't want to do yesterday because it was starting to get tired, and I want to enjoy this. Why are you programming on a Mac? What's wrong with you? Real people use Linux, B close parentheses. I guess I'm not real people. I have Linux, by the way. It's here. It's in a virtual machine. I use it sometimes, but right now I'm not using it because when you're doing ray tracing, it doesn't really matter much whether you're on a Mac or Linux or Windows. So yeah, I don't know. In any case, thank you for your comment. In any case, very enlightening. Thank you for having contributed to the discussion. So positionable cameras, like the electrics, are a pain to debug. So I always develop mine incrementally. First, let's allow for an adjustable field of view, the FOV, which is it's the distance from, yeah, how do we define this, by the way? Wait, I think we, you know what? I'm going to take a moment. Since there isn't too much stuff in front of us, let's take a bit of time to try and understand these concepts, maybe with a little bit more depth than I did in the other 2 days. So we started by defining a camera which sits at a point, and then, so this is where the camera is. There's a distance between us and the viewport, and the viewport is, so it's this like space in front of us in terms of the camera, and I guess it's the section of the space that we decide to sample on. So it's kind of the stuff that we quote unquote see from the camera, which is then what we report on the image once we write down what we sampled. So the focal length is then the distance between us and the viewport, I believe. So what does it mean to change this distance? By the way, I don't know what it means, but we can mess with it and see what happens. So what happens if we're not at one, I think we were at what, one unit of something, let's say 1 meter from the viewport. What if we're not? What if we're somewhere else? So where do we do this stuff? Focal length is set to 1, and we use it here, and then we make focal 3. And what is focal 3? We use it to compute the camera center, which then we use it to compute the viewport upper left. Okay. Do you have Twitch and YouTube chats merged? Maybe. Depends who's asking. So let's say that focal length is actually 2. And so probably, by the way, the fact that the book is pointing this stuff out later on, it means that there's probably some other math that we should implement to make sure that all of this makes sense. And probably changing this number without having the rest of the stuff implemented will make it misbehave, but let's watch it misbehave. Let's see what happens. Maybe I could reduce a little bit the resolution, huh? 4K is a lot. Somebody was pointing out that there are apparently numbers between 400 and 4000, and I could choose some in between number, which is fair. Maybe that's what I will do next. Okay, so right, by increasing the number, I moved closer. I think that what's happening here is I think we literally just moved closer, right? Can you spawn a process node for each row so we can see a nicer progress? I mean, that's what you're seeing. Like the number that you're seeing is the number of rows. And you see the number of rows that as I'm completing them. If you want, like if I spawn one, so you want one per like pixel basically. In any case, let's try to find a number between 400 and 4000, huh? So we can do 1980. Still seems fine. Okay, what happens if we get further away? What if instead 2, we're now at -2? So hopefully this, I was about to say, hopefully this doesn't break anything, but this has broken something. What is going on? Why don't we see anything? What if it's 0? There's also some, I think we might have done something bad. I think there's like, is this like infinite FOV? What if it's 0.1? So probably negative doesn't work, huh? Yeah. Still, I don't have an intuition for what exactly is causing this stuff to distort this way. I get it. I've messed with the FOV value in games, and so I'm understanding this now. So basically, yeah, we're fishying a ton. But what is exactly the point? Because we basically have a viewport in front of us, and we are moving it either closer. So when we set it to 2, we moved it closer to us. And then we set it to 0, it was infinitely far away from us, pretty much. And here it's very far away, but also, yeah, very turbo fish eye. Also, what if this is 10? I'm guessing that going up in numbers just gets you closer to the scene, but you don't really. Oh man, yeah, we're turbo zoomed into the center ball, huh? Like we're definitely enjoying the center ball a lot. Okay, so 0.5 is probably FOV, but still a reasonable number. Okay, I'm guessing the book was gonna give us some information about this math. Let's see. Okay, let's go back to chapter 12. Okay, so since our image is not square, the FOV is different horizontally and vertically. I always use vertical FOV, and I also usually specify in degrees to change to radians inside the constructor, a matter of personal taste. First, we'll keep the rays coming from the origin and heading to the z equals -1 plane. Let's see. Camera view in geometry. We could make it the z equals -2 plane or whatever, as long as we made h a ratio to that distance. So here's the setup. So this is where the camera is. Y goes up, X goes right, Z goes inside. And we're saying that we're making it the -1 plane. Okay. And so we parameterize by H. So what we care about is this number here. And so that derives where the camera is placed, because we said that we set the Z plane at a particular position. We want to parameterize by H, and consequently that forces us, well, that decides where the center goes, right? Let's see. So we have FOV, vertical view angle. Oh, I know this number. 90 is not a great FOV. 120 is usually what you want to have in a frenetic shooter, right? Let's see. FOV. It says vertical FOV. 360 is even better. Yes, sure. But usually engines don't allow you to do that. They don't allow you to see behind yourself. Okay, so we have FOV. I think this has replaced focal length. I'm kind of sad to see focal length go. We just made friends right now. In any case, so now we have theta, degrees to radians, and then viewport height is formulated based on that, and then everything else is still the same. Okay, let's see how that looks like for us. Viewport height. Where do we do viewport height? Oh no, we had a hard-coded viewport height, which we can't have anymore because now it's parameterized. So that means that this needs to become a block. We do the math inside. Constant theta, degrees to radians. I think we have this in math, right? Maybe I'm just too optimistic. Let's see. Degrees to radians. Rad from deg. I made this up. We don't have it. Deg to rad. Rad. Oh, we don't even have that? Really? Math doesn't have it? We have rad per deg. Degrees to radians. Yeah. Okay. So degrees to radians, but it accepts on any type. This makes me think that this FOV needs to be defined as a F64. So constant H is tan. SED math tan of theta divided by 2. And then we break BLK with this. Okay, this is the vertical FOV. Oh shit, we still had focal length. Wait, what? We still have focal length around? Really? Okay. I thought that this would go away. Never mind then. Also, you know what? This doesn't have to be an F64. This just needs to be 90.0. Ambiguous conversion of division operands, comp time float and comp time int. Okay, are we still good? It seems that we're still good. What if this FOV is now 120? Yeah, there we go. Now I can see people coming from behind the corner and shoot them as they try to flank me behind the behind the metal ball. Okay. We'll test this out these changes with a simple scene of two touching spheres using a 90s field of view. Sorry, a 90-degree field of view. I mean, I'm not gonna do it because as much as I love the MasterCard logo, we just tested it right now. Like, I don't know, guys, if you can see this in chat, but if you played enough shooters, you can feel it, the difference between 90 FOV and 120 FOV. So yeah. Which language is this? It's Zig. Yeah. Welcome to the stream, by the way. So I'm gonna skip this test. I'm fine with what we have. If we're gonna need this also in the future, then we can come back and actually do it. But I'm happy with this test already. This to me seems clear enough already. Yeah, it's ray tracing in one weekend. Exactly. Welcome to the stream. Let's see, positioning and orienting the camera. So by the way, Zig, just very quickly, you can go to zigline.org and maybe zoom out if you're super zoomed in as I am. And you can learn more about the language. It's a lower level programming language. I'm doing ray tracing in a weekend, and I'm not following any of the OOP advice, and I'm actually implementing this in a better way. So this is, I guess, the main contribution that I'm making to the population of people that have done ray tracing in a weekend. This has been super easy and fun in Zig. Obviously, if you don't know Zig and if you're not used to lower level programming, you might end up with questions that kind of distract you from the core point of ray tracing in a weekend. But as soon as you gain a little bit of familiarity with how to do manual memory management, it's very nice and easy. Let's see, after 12 hours of playing Quake 3, I was feeling the difference. Hell yeah. Yep. Especially if you have also the modifier that turns every enemy into orb. I used to do this. I think it was, is it orb with 2 B's? Quick 3. Yeah. I had a modifier that made every enemy orb. So funny. In any case, okay. You can set that in the config. To get an arbitrary viewpoint, let's first name the points we care about. We'll call the position where we place the camera look from, and point we look at. Okay, later if you want, you could define a direction to look in instead of a point to look at, which is fair. And why can we not do this right now? Because it's probably some extra transposition that we're just not doing. Like, I think that if I were to move the camera, let's move the camera at random, see what happens. But I think that we don't have a way of like angling it, right? So how do we move the camera? I think that where we make at some point we make focal 3 and we say viewport upper left is this. Well, what if this wasn't 0, 0? What if this was 0 0.3, 0 0.2, 0 0.5, whatever? What happens now? Yeah, we just moved a little bit on all 3 dimensions, but we haven't done anything interesting with this. So, okay. Yeah, so I was able to move the camera, but I wasn't able to really change the direction. Sorry, really change what I'm looking at, because I'm guessing that has to do with the math that we do to decide this, I believe, which is parameterized by this, yes. But I think let me think about it for a moment. So let's say that we wanted to have this camera point a little bit down. To do this, we would want this vector to point. It already points kind of up left, right? So we would want that vector to point in a different direction. And then we build the rest of the viewport from there, right? So viewport upper left should be independent of camera position to move the camera freely. Really? You know what the problem is? We have the problem. Well, one of the problems is that we have spheres. If we had some other shape, it would be easier to understand if what we're doing is smart or dumb. But okay, let's do an example. Let's say that this is XYZ, right? So let's set Y to 50. So this should put us very high up. This has not put us very high up. What happened? Why am I here? Where am I? This has not worked as I was hoping. Okay, let's set the FOV back to 90. But also, why is it like this? Okay, minus 50. What happens with minus 50? It's all very blue, which matches. Okay, I guess our Y is pointing down somehow. The video doesn't do that. The book seems to explain that Y is pointing up. So I'm surprised that we giving here a negative value is what moves us up. So the reason why it was yellow is because we were going down, and I think we were looking at the giant yellow sphere, and now we're going up. Let me try a less extreme value. 10 might be still be too much. Let's try something like 3 or 2. I think we basically should see. I'm gonna keep doing this until we see basically the spheres. Just there we go. Just some of the spheres, right? So now we're going up. We went up. The spheres are below us. Now, what I would like is from this position, I would like to look down. So how do you do this? You do this with vector. With a vector sum. I think we might need more math. By the way, this is what the book is about to teach us. So I'm curious to try and freestyle this a little bit, but then I'm gonna give up if I go nowhere, and I will just let the book tell me. But it seems to me that if we can now convince this vector to point down the right amount, and maybe we don't have a good way of deciding what this amount should be. Like the book was providing us with a very well-structured idea, like this is the point that you would be looking at. And then if you want, you can decide the direction. And right now we don't know how to express this. But So if we add these, whatever this vector is going to be, and we add it with another vector, how do we say, let's add this with a vector that looks down. A vector that points down is a vector that does 0, 1, 0, right? Oh, god damn it. This did not work as intended. Oh, wait a second. No, maybe it did. It's just that this is pointing in the wrong direction. No, maybe it was right. I don't know. Maybe 1 is too strong of a component. Yeah, no, okay, so I see what happened. No, never mind. This is wrong. This is the wrong operation. Because what we're doing is we're basically compensating what we did here. Oh, there we go. This is why it's backwards, because we're subtracting this value. Okay, stuff is starting to make sense. There's no mistake in the directions, but the fact that in the final formula we subtract this vector here is why if we want to go up, we need to put a negative number. If we want to stuff it in there, if we don't want to stuff it in here, so if we leave this like this, then here is where we go up. I think. Yeah, this leads us back up here. But the problem is we have no way of expressing angling. Okay, so I'm gonna give up and let the book tell me. Let's see. Yeah, how do we do this stuff? Let's see. We also need a way to specify the roll or sideways tilt of the camera. The rotation around the look from axis. Another way to think about it is that even if you keep look from and look at constant, you can still rotate your head around your nose. Yes. What we need is a way to specify an up vector for the camera. I think, Akras, that you might have, maybe what you were saying makes sense. I'm not sure. We'll see. But yeah, it's definitely something more that we don't have right now. So we can specify any up vector we want, as long as it's not parallel to the view direction. Project this up vector onto the plane orthogonal to the view direction. So this is the view direction in front of me. I have some up vector, and then I need to project it. No, on the orthogonal plane. So I project it, okay, on this plane. So I get a tiny vertical vector. And we're going to name this the V up vector. After a few cross products and vector normalizations, I think this is what the operation that we were missing. It was a cross product. I'm guessing this is like very vertical. What is happening? Oh, there we go. Let's see what happens now. Yeah, there we go. Okay. I'm not sure we have obtained what we were hoping to obtain, but something has definitely happened. Look at that sphere down here. Okay, let's make this maybe -1. This we can leave positive. I don't know what I'm doing. Okay, so maybe this should be -3, and this is -3. What happens now? Hello, Rock Rager. Okay, yeah, we're going kind of whack with this. Okay, but cool. So for now, no vector product. Well, we'll see what we do next. Okay, in any case, we now have a complete orthonormal basis UVW. To describe our camera's orientation, U will be the unit vector pointing to the camera right. V is the unit vector pointing to camera up. And W is the unit vector pointing opposite the view direction, since we use right-hand coordinates. And the camera center is at the origin. So let's see, look from, and then we have a V up, and then we have V, U, camera view up direction. So, and then we have V up, and then W. I'm not sure I understand what the heck W is supposed to be. If you have complete orthonormal basis. Okay, so this is the idea. So you come up with a V up vector, and then you break up the V up vector into 3 vectors, I believe, which are U, V, and W. And each one of them only has in it one component of the original V up vector. Okay. And I guess we need that then for our competitions. So our knobs are look from camera position, look at a point in front of us that we want to look at, which means that we want to have for it to be at the center of our scene, something like this. Not our scene, sorry, at the center of our view. And then V up, camera relative up direction. Okay, yeah, what the camera considers to be directly above it, which it's a way of saying tilt. Okay, cool. Okay, so we take, but aren't these 3 guys literally these 3 components? Maybe not. Oh, no. No, I think they're not. This V up, okay, I think that this V up is just a way of like isolating, I think, one component. But then these calculations are also based on this. We also need to factor in these guys, I think. Okay, let's see. So under the FOV, look from, look at. Um, 0001. Wait, was it 1 or -1? -1, yeah. And then V up is 010. Okay. Okay. Then we have these 3 components, and where do we use these guys? So center is look from. It's not 0 anymore. Oh, about that. Camera center, huh? I forgot about that. Okay, so center is look from, which is still 0 for now, but now it's parameterized. And then focal length is look from minus look at length. Okay. Actually, this is just magnitude, not squared. And then this one's to calculate UVW. And where do we use UVW? Yeah, to calculate the upper left quarter. So how does it work? Center. And now there's a multiplication. Yeah, the formula is slightly different, huh? But, so I see that we need W. Cool. U and V. Where do we use these ones? Oh, here and here. Okay. So we use this stuff to calculate viewport U, viewport V, and then viewport upper left. Viewport U, viewport V. Okay, so these guys need to be here. Times U times minus V. Okay, then upper left is this guy. This is going to require some splatting, I think. Oh, this is also, well, wait. No, we already did this. Did viewport 2, U, viewport V divided by 2? Yes. This is correct. Then focal was previously this value. Now it's focal length times W. Okay. So camera center minus this, minus this, minus this. Okay. Shows declaration of W. Oh, we have too many W's. God damn it, this WVAC. And we're looking into nothingness. Did I mess something up with the numbers on my own? This is normal. This is okay. This is okay. This is okay. This is okay. The rest I think I copied. Oh, do these guys get initialized the same way? Wait a second. Yeah, I think I need to change them, don't I? I forgot to do that. So it's viewport width and viewport high times U times minus V. Why do I feel like I've done this already? The U and the minus V thing? Oh, I did it here. Oh no. I think I might have touched something that I shouldn't have touched. I was supposed to touch viewport and not pixel. So this was fine. Oh no. Okay. Okay. So this is, so this is this. And this is viewport width. This is height, I think. And this is divided by EMG height, EMG with, I guess we'll see if I swapped width and height somewhere. So there's a scalar. Okay, what is a scalar? UVec. Oh, that's a vector, and that is, okay, yeah, we need to splat. What is your opinion of the Ladybird browser project? I think it's interesting that there's a new browser being made. I think it's good. I think that we shouldn't let an ad company. Oh my god! Wait a second. I think I swapped around some height and some width. Give me a sec. U is width, V is height. Yeah. Okay. So I think it's good that this is happening. I think that Andreas Kling is an interesting project lead for something like this. I do think that Ladybird will have to prove itself in terms of performance, because browser performance, I think it's not easy. And it's also something that I strongly suspect everybody bungles because they go ham with OOP isms. And Ladybird is not rejecting OOP isms. In fact, it's a C++ project that is transitioning to Swift. And if I have to be honest, none of these languages, like neither language, is blazingly fast in my mind. You can obviously use them to good effect and get good performance. Not saying that it's impossible, but it's a different, like, for example, Zig exists in a different category of programming style, and this is probably not going to be the style that Ladybird will use. So, and if I think about projects that I've seen from Andreas Kling, in none of them performance has been the main focus. They have never been mind-blowing from the perspective of performance, because that was not his intent. So I'm not saying that this is a failure of any kind. We don't know. But it's something that we don't have. At least I haven't personally seen data points in the past. That said, Andreas used to do performance work back when he worked at Apple on WebKit, so it's not like he doesn't have experience. But as I said, it's just something that I haven't seen. I've seen Andreas lead a project. I've seen Andreas, collect, get funding for Ladybird. I've seen a lot of things that I think Andreas has already given ample proof that he knows how to do well. The performance part is non-trivial and something that is, to me at least, a bit of a bigger unknown. That's it. But overall, I think that Ladybird is good. I want to see it succeed. Also because I don't like Firefox. I have a ton of beef with Firefox, and so I need somebody to make something better. Performance or functionality hard choice. What do you mean? Why does it have to be a choice? Why do you put yourself in a dichotomy where you don't have to? You can have both. You should have both. You should aim for having both. Like, for example, in Ghosty, is it performance or features or functionality? Like, what? That's not even what? Ghosty has both. Ghosty is performant and it has features. Is it the most featureful terminal emulator on the planet? Probably not, but it has features and it's getting more. And so let's see. Okay. We'll change back to the prior scene and use the new viewpoint. we didn't modify our scene, so it's easier for us. It's easier for us to do that. Oh, there we go. We're finally able to move our camera. So how does it work? Look from is -2 to 1. Let's do that. And look at is 0, 0, -1. Okay. And up is 1. Okay. Let's see what happens. Yeah, there we go. We're finally able to look stuff from above. Yeah, so we needed a bunch of math. We needed definitely more math than what I was intending to put in on my own. You know what? I wish I was less rusty with these things and I had a stronger handle in order to be able to do this stuff on my own. It's unfortunate. I'm a bit rusty. Eventually, I will probably need to go through a refresher of all these things. We can change the field of view. Of course, FOV 20. Disgusting. I'm not going to do it. FOV 20. So first of all, at FOV 20, you have the problem that the natural bobbing, when you move your character, if it's Quake, there's not a problem. But like if it's Call of Duty, now the sway as you move, way too much. Absolutely, it's impossible to understand what's going on. So I'm not going to even attempt FOV 20. Horrible. I leave at FOV 120. Period. 120 gang. Let's see, defocus blur. Now our final feature, defocus blur. Note, photographers call this depth of field. Or there's an even better term, bokeh. The bokeh. Ooh. Which you can actually see also here on my camera. Look at my hand and look at me. Look at all the bokeh. So the reason we have defocus blurs in rear cameras is because they need a big hole rather than just a pinhole through which to gather light. A large hole would defocus everything, but if we stick a lens in front of the film / sensor, there will be a certain distance at which everything is in focus. Objects placed at that distance will appear in focus and will linearly appear blurrier the further they are from that distance. You can think of a lens in this way. All light rays coming from a specific point at the focus distance and that hit the lens will be bent back to a single point on the image sensor. We call the distance between the camera center and the plane where everything is in perfect focus the focus distance. Be aware that the focus distance is not usually the same as the focal length. Yes, the focal length is the distance between the camera center and the image plane. I think in the case of cameras, the focal length is the distance between the lens and the sensor. And the focus distance is the length between, I guess, the lens and the point where the point has the property. Although, is that a property of the lens or of the image sensor? That part I'm not sure about. No, I think it has to do with the lens. I'm starting to learn Zig and I'm using AI, but going through each step of the process very thoroughly until I understand what the code is doing. I'm using AI to have everything placed in one place. If you want a suggestion, Lyle, I mean, if AI is giving you satisfactory answers, fine. Although be aware, obviously, that, AI sometimes doesn't know, but it will still sound very convincing. And it will tell you sometimes things that are not entirely wrong. There's wrong, which you can trivially understand that is just not working and the AI is wrong. But sometimes the AI would also give you ideas that sound correct that you cannot immediately right away tell that they're wrong because you don't know and because they kind of work. So for example, you ask, how do I do X? And then the AI gives you a way of doing X that is completely out of whack. It works at the end of the day, but it's far from the optimal way of doing it. And so you might not realize that that is a very whack way of doing that thing because it works, and in front of you, like the only point of comparison that you have is the AI itself. So with that in mind, consider joining a Zig community where you can see also other people do work with Zig, write Zig, read. You can read what they write. You can share what you've wrote so they can comment on it. And that gives you more perspective. Unfortunately, what I just described as a problem with AIs is that the same problem also applies to people. People can give you bad ideas. And if you're in a community where a lot of bad ideas float around and are considered the correct way of doing things, then you will internalize a lot of bad ideas. There's no escape from that. But let's just say that usually humans are not all trained on the exact same data set. And so they tend to have conflicting ideas, and then they tend to converge to something better when they are able to voice their different opinions and etc. In any case, let's see. So this stuff, focus distance, focal length. Let's see. We call the distance between the camera center and the plane where everything is perfect. The focus distance, yes. The focal length is the distance between the camera center and the image plane. Yes. For our model, however, these two will have the same value, as we will put our pixel grid right on the focus plane, which is focus distance away from the camera center. Okay. In a physical camera, the focus distance is controlled by the distance between the lens and the sensor. Film/sensor. When was this written? No, I'm joking. You can do film also today. This is why you see the lens move relative to the camera when you change what is in focus. That may happen in your phone camera too, but the sensor moves. Yeah. The aperture is a hole to control how big the lens is effectively. For a real camera, if you need more light, you make the aperture bigger and it will get more blur for objects away from the focus distance. For our virtual camera, we can have a perfect sensor and never need more light. So we only use an aperture when we want the focus blur. I mean, people also want higher aperture numbers for lenses just because they want the out of focus effect. Sorry, this is I'm not saying that the book should. I'm not contradicting the book, and I'm saying that I'm not saying that the book should get into these details. But the reality is that even though yes, camera sensors are imperfect, people like the out of focus effect. They chase that. People pay extra to have a lens that has the ability to open wider than other lenses, not because they want to be able to shoot in lower light settings, but or maybe that's also a factor. It can be a factor, of course, but also because they just want to be able to have more bokeh. And the problem, though, is that this is something that the book hasn't mentioned at all. But what normally happens is that you don't exactly have a focus plane, or rather, yes, you have a focus plane, but for practical purposes, what you think about is more like a focus, not just one vertical line, but it has some depth. So you have basically a section of things that are in focus, and then of course at the center of it is the perfect focus, and then it degrades as you get more away from it. But in practice, you will have a space where and you can. I'm showing it to you like this, but in reality, from the perspective of the camera, it's like this. It's like rotated 90 degrees. It's rotated 90 degrees, and you move it back and forth as you change the aperture. And the problem is that the more you open the lens, the more. Sorry, I'm saying something wrong. No, it's you don't move it by changing the aperture. You move it by moving the focus ring, by moving the lens back and forth. But the aperture, like literally how big is the iris open, the more you open it, the more this thing becomes thin, the faster things go out of focus as you move away. And you can get to an extreme where you can even have the focus plane being so thin that you cannot have a face in focus. There's lenses that have aperture values of like 0.8 even. And those things are basically impossible to use for portraits or like for shooting heads, because they are so thin that you would have like the person's nose in focus and then their face would not be, or the face is in focus but the point of their nose is not and their ears are not. If you want to see some of these, this is something that I remember finding kind of funny in the past. Molly Rocket. One thing that I found funny about Casey in the past is that he has some of these older videos post handmade, but I think it might be one of those. I'm trying to think. Maybe it is one of those, maybe not. Maybe it's still from here. Let me see this one. So he had this problem because you could see that he was using, let's see if he ever goes full screen in this video. Yeah, I would need to find one. There are some videos where you can see him full screen. Maybe it's these ones. Let's see. Let's try this one. Where to me, it felt like that he was going way too overboard with the autofocusness. Yeah, you can see, like, look at this image, okay? Let me try to make it bigger. I think you can see that his ears are out of focus. This is not just me, right? You can see that there is bokeh on his ears. You can see way more details on his face. Here you can definitely see, all the skin imperfections. But then when you get to the ears, they are out of focus. This is way too much. This is way too much. So something to be on the lookout for. That said, you can also see something else in this image. You can also see that he's doing lights with LED strips that do things. There's some LED strips in front of him, positioned in a way that doesn't make too much sense, in my opinion. And there is no way of diffusing the light. So the light is not diffused at all. And you can see that it makes parts of his face light up a lot in a way that you feel it's a little bit too harsh, in my opinion. You can really there's this technique of literally placing the objects that diffuse light in front of light sources, and that makes the light softer. And here he's not doing this, and not only you see this in the reflection on his glasses, but you also see it on his face that this light is like, it has some very clear points where it's very strong. And if you had put some diffusing system, you can have like cloth, like you can have a white sheet of some textile material, or they also sell umbrellas. There's like these tiny umbrellas that are all white and translucent, and you basically put them in front of the light source, and they help you soften the light. But in any case, so he had this setup, which I believe was also so another reason why he had this extreme bokeh is because he was probably like, these LEDs are probably not making too much light. They're not making a lot of light. And so he probably wants a very open lens in order to have enough light in the image. One last thing about light, which is interesting that the book doesn't mention, is that in modern cameras, you don't always resort to opening the lens more if you need to get more light, because opening the lens changes the bokeh, makes the focus plane thinner, for it's a practical description. In practice, that you can't make a plane thinner, but if you listen what I mentioned, what I said earlier, it does make practical sense. And so because of these reasons, what you do is you bump up the ISO value. So a sensor can literally have a let's call it that you do, let's say that you do basically electronic multiplication of the intensity of the light that the sensor receives. And so you can obtain more light without opening the thing. Well, not more light, but like having what's the term, man? I'm like missing some key terminology. But in any case, you can have a working image using ISO. The problem is that sensors are imperfect. They also get noise. They get noisy. And so if you bump up electronically the numbers that they read, and there is basically not too much there, if the difference between actual light that is real that goes into the lens versus the noise that is internal of the sensor, if there is not enough distance, your noise becomes, your image becomes completely noisy, which is actually not too different from how it is for you when you try to see things at night and you can't really see it. Your brain processes this stuff, so the way you perceive it is not exactly the way you see it play out in cameras, and also your eyes aren't camera sensors. There's a ton of differences in how these things work. So I guess my point is that it's not a one-to-one comparison, but the core problem is the same. You need a signal from the outside, like the light, and if you don't have a ton and you have a very little, then noise, it's harder to tell apart the signal from the noise, basically. And both your eyes at night and camera suffer from the same problem. In any case, long story short, I'll conclude here with this. Here's my heartfelt recommendation. Don't do what Casey does. Don't use random lens position in weird position for lighting. Do not open your lens to the point where your ears are out of focus. It's weird as fuck when your head cannot be entirely in focus. It's super weird. Also, keep in mind that the camera needs to do tracking of your face, and it will try real hard to keep you in focus, because as I was saying, the lens needs to be repositioned to keep you in focus. So the camera can do tracking. Like the camera is doing tracking on my face right now. Look at this. I move, you see? The camera is tracking my face when it can see it. When it can't, then it will put in focus the thing in front of it. So if your face can't fit inside in focus, what will happen is that sometimes your nose will go out of focus. It's weird. Ears out of focus is nice looking, actually. I mean, beauty is in the eye of the beholder, for sure. I think it's not a great way of doing it, to be honest. This is why horse portraits are so hard. Wait, Crypto. So this is an amazing comment, but also, are you serious about it? Because I think I think that you're pointing at something that is actually genuinely true. Provide a sense of that compared to having everything be crystal clear. Yes, of course, but you want the background to be out of focus. You don't want to be half of your face to be out of focus. It's insane. That part is, in my opinion, is insane. And to be fair, it is correct to say that there are some subtler aspects of the language of cameras and shooting that really, then if you're not really used to thinking about them, you think and you're presented with these differences, you don't really think about it much, and you say, actually I don't care. So to be fair, you can do it. It's not the end of the world. Like Casey has done it. Does that mean that his video is unwatchable? Not at all. Not at all, of course. But those things are real, and the amount of effort that is put into getting all these things right is not wasted. It really does make a difference in the grand scheme of things, in my opinion. I've personally believed these based on my experience trying to understand how to do video and stuff, like video production for for events, or even this case, by the way, I have a camera in front of me with a pretty decent lens and a decent lighting setup. Basic, but decent. That said, the general principle is that you want separation between the subject and the background. In this scene that where you're looking at me right now, you see me, and you have a separation between me and the background. You also have separation between me and the microphone. It's actually debatable if the separation between me and the microphone is something that you want or not. But in any case, I don't have a half out of focus head. Like, I think that is too much. In any case. If someone wanted a better but not necessarily streamer quality video setup, what's the best route? This answer is not gonna stay true forever, but I believe that still today, the answer is that you want to get a cheap DSLR, an older generation DSLR that is super old and cheap, and don't go with webcams. My point is, in my opinion, definitely a flat, at least up until a few years ago. So I'm not up to date with the latest and greatest in webcams, but up until a few years ago, not even that many, let's say up until at least 3 years ago, without a doubt, the best, highest quality webcam is worse than one of the cheapest DSLRs, sorry, not DSLRs, mirrorless cameras that you can get. So the idea is that you get an older camera. You basically give it a fake battery. You can buy, it's super cheap, a fake battery that basically works as a power adapter. So you put it this fake battery, it has a wire that comes out of it, and you connect it to a power outlet. And then you have the camera send you the video signal that you can then capture with either a capture card, or if the camera is not super turbo old, it can even do directly camera to USB in your computer. So it can send the video signal over USB. That said, I think that the camera to USB thing is something that works well in newer cameras. And in reality, if you want to be cost efficient, it's better. It's easier for you to do older video camera to capture card. The reason why an older video camera is good for you is because you don't have to, you don't care about almost any of the newer functions or of the things that have been improved in recent cameras. For example, stabilization. This is a thing that has improved a lot in newer cameras, and that it costs a bunch. And you don't care because your camera is gonna sit on a desk. Low light, ability to do stuff in low light. You don't care because your setup is gonna be pretty much constant. The worst thing that you can have is a window next to you. But that window will add light. It will not subtract light. So you can, I'm assuming you will have the ability to, shut off the window to make sure that you have a perfectly normalized setup that doesn't have any changing variable. But you don't even have to. What I'm saying is that even the worst case is actually, it doesn't require you to have a better camera. So you pay, I don't know, like a few $100s for that camera, and then you pay a few $100s for a lens, and you're pretty much good to go. Like your setup, and that setup will last you for a long time, and you will get a very high quality image, which will also be 4K. So if you're 4K ready, you'll never have to upgrade until the things breaks down or you decide to buy a newer camera. I have a couple cameras. I started with this. It's a Fuji X3. I like it. I don't regret starting with Fuji. My recommendation nowadays would be get a Sony camera. Get a cheap Sony camera and do that. Last thing, in reality, the thing that makes the biggest difference is not the camera, but is your light setup. You need to have 2 lights. You need to have a a main light, a second light. You need to have diffusion in front of them. Don't do the thing that Casey does where it looks like he's like being abducted by aliens. And by the way, I'm being kind of harsh on it because he also made a video telling people to just buy LEDs and use those. I think that's terrible advice. I find it funny that he complains about people giving other people terrible programming advice as he's giving people terrible camera advice. Let's see. KZ LED. Let's see if it shows up. Oh my god, I'm misspelling his name horribly, huh? Not LED camera. Let's see. He has a video where he tells people how to record stuff. Yeah, the FX3 is nice. I don't have an FX3. I have an AS7 III, which is basically the FX3, just less cool. I didn't get the FX3 because I didn't want to spend the extra money for the cinema version. In hindsight, I should have. In hindsight, I should not have gotten AAS7S3. Should have gotten an FX3, but oh well. Video setup. I don't remember. He has a video on how to do the recording setup. Maybe I should say lights. Although there's a bunch of light stuff also in Handmade Hero, so there's gonna be a bunch of that. In any case, sorry, I can't find it, but he has a video on how to do the camera stuff. For the love of God, don't do that. Let's see, I only do indie cinematography and photography, so I like when it's all grungy looking. Don't hire me for a professional event. This sounds like too much work. Yeah, well, it depends on how much you care having a good image. It depends on that. In any case, let's continue. A real camera has a complicated compound lens. For our code, we could simulate the order sensor, then lens, then aperture. Then we could figure out where to send rays and flip the image after it's computed, because the image projected upside down on the film. Graphics people, however, usually use a thin lens approximation. We don't need to simulate any of the inside of the camera. Also, sorry, one last point. Rocco Rager, here's one last piece of advice. Another way of getting something cheaper is to get an APS-C camera. So you have full frame and APS-C. Well, you also have, this is like the sensor size of the camera. You also have different sensor formats and shapes. But let's say that the two main ones are full frame and APS-C. The difference is, for the purpose of what we're talking about, cost. So if you get an APS-C camera, it's going to cost you less. The nice thing about Sony is that you can buy an APS-C camera and a full frame lens. So usually when it comes to cameras, the lens tends to last you more than the body, because the body has a bunch of electronics in it that becomes obsolete after a while. It also has software. You know how disgusting software is. It starts smelling bad like 3 days after that you leave it out of the fridge. So the lens, well, I was about to say the lens doesn't have any software. That's actually not true. The lens doesn't have as much software, so it tends to be good for longer. So the idea is that you have lenses for APS-C cameras, and for example, for Fuji has an APS-C system normally. So your lenses will be for APS-C. And there's not a ton of interoperability. Lenses for different brands don't work on other cameras unless you use adapters, but there's a ton of downsides. And when a brand produces both APS-C and full frame, not always lenses for one system work for one, let's say, sensor size work for the other sensor size. And not because of real technical reasons, but mostly because they just make a different attachment and you just get fucked. So for Sony, one nice thing is that you can buy an APS-C camera, you buy a full frame lens. Then what you do is that you can use it, and then when you decide that you want to be more serious about camera stuff, you can take your full frame lens and use it on a full frame camera, assuming that the upgrade for you is worthwhile. In any case, let's see, we don't need to simulate any of the inside of the camera. For the purposes of rendering an image outside the camera, that would be unnecessary complexity. Instead, I usually start rays from an infinitely thin circular lens and send them towards the pixel of interest on the focus plane, which is focal length away. So let's see, here's the film, well, here's the sensor, here's the lens, here's the focus plane. Okay, so let's see, I usually start rays from an infinitely thin circular lens. So the rays start from here, they go here, wait, what am I missing? 20 years ago, wasn't that during the Napster days? What specifically? Films? You mean? Like film cameras? Is that what you're talking about? Let's see. So we start on... Oh, the Sony Rootkit thing. Oh. Okay, so we start from here, blah, 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 where everything on that plane in a 3D world is in perfect focus. In practice, we accomplish this by placing the viewport in this plane. Yes, putting everything together. The focus plane is orthogonal to the camera view direction. The focus distance is the distance between the camera center and the focus plane. The viewport lies on the focus plane, centered on the camera view direction vector. The grid of pixel locations lies inside the viewport, located in the 3D world. Random image sample locations are chosen from the region around the current pixel location. The camera flies rays from random points on the lens through the current image sample location. Okay. Generating sample rays. Without the focus blur, all seen rays originate from the camera center. In order to accomplish the focus blur, we construct a disk centered at the camera center. The larger the radius, the greater the defocus blur. You can think of our original camera as having a defocus disk of radius 0, so no blur at all. So all rays originated at the disk center. Right. That explanation, I think, tracks with how it works in reality, because I think in reality the problem is that you have a lens, and a perfect lens would be able to make all light rays converge to the center of the lens perfectly, no matter what the aperture is. But in reality, lenses are imperfect, and what happens is that, especially as you open, the lens ability to bend everything correctly and collect everything and move everything in the right position, it just doesn't happen. And so some rays end up hitting off center, and it is part of what causes the blur, I believe. So how large should the focus disk be? Since the size of this controls how much the focus blur we get, there should be a parameter of the camera class. We could just take the radius of the disk as a camera parameter, but the blur would vary depending on the projection distance. A slightly easier parameter is to specify the angle of the cone with apex at viewport center and base defocus disk at the camera center. This should give you more consistent results as you vary the focus distance for a given shot. I'm not sure I follow this explanation. Since we'll be choosing random points from the defocus disk, we'll need a function to do that. So random in unit disk. Okay. This function works using the same kind of method that we use for random unit vector, just for 2 dimensions. Okay. So random double, and the third one is 0. Okay, so let's go add that to our vector class. Our vector class is becoming kind of vector class. What am I talking about? To our vector namespace. We're starting to have some very specialized operations in here. Like some of them are generic enough that make sense to have in a vec thing, in a vec namespace. Some of these are I'm not so sold on. So maybe would belong in the camera, I think. But you know what? I'm not a C++ programmer. I don't know how to write clean code, so don't listen to what I say. What is it? Random. Oh, also this is one of the random functions, so it goes at the bottom. I mean, we already have random hemisphere, so might as well have random disk, huh? I think we can steal the code pretty much. So while through const is a this is random range, and this is also random range, and we need to pass in R. Okay, so this is the implementation. Now let's update the camera to originate rays from the defocus disk. Okay, variation of angle of rays through each pixel. Distance from camera looked from point to plane of perfect focus. Okay. The focus angle, focus distance. What was the focus angle? 0. Okay. Then the focus disk UV. Okay. Oh, look, we have a diff where we can see that a line was deleted. Interesting. I guess they had to tell you because otherwise you wouldn't necessarily immediately realize this thing is not being used anymore. In our case, life is going to be better than this. So let me show you. We need to initialize this focus disk V and this focus disk U. Where do we initialize them? Down here. Okay. In any case, we don't have focal length anymore. And you can see that because, so viewport height is 2h focus dist. So viewport height is 2h focus distance. And we still are using focal length, are we? Yeah. What is disk? Disk is a simplified model of a camera lens slash aperture in order to introduce autofocus. Like, you know, the fact that you have something that is in focus at a given distance and then everything else is out of focus as you move away from that plane. So right now we're using it in here to define focal for viewport upper left. I guess that's also going to change. Okay, so we fix this. Let's fix viewport upper left. It's center. Now it's focus distance times W. Focus distance times W. There we go. Okay. Now we need to do this stuff. Oh, and yeah, focal length is not being used. And I was thinking that it would give me a news variable, a news decal, but unfortunately we don't have a news decals yet. Wouldn't it be a sphere? So no, normally lenses aren't spheres. But I think I understand what you mean. But I think the point is that we're not really, we're not really simulating it fully. We're basically just using it as a model for where to put the knobs, basically, in order to obtain an effect that looks realistic, given what you would normally see like on a real camera. But the point is to bypass real simulation of what happens with lenses and instead just resolve these things in a more analytical manner, if that makes sense. That's at least how I'm interpreting what we're doing. Okay, defocus radius. Where do they put it? At the very end. Okay. Oops. Okay. So we have all of this stuff. And now in get ray, the ray origin is different. And then defocus disk sample returns a random point in the camera defocus disk. Yeah, okay. So the ray origin, which we're doing everything backwards. So the reality is that what we're doing is a ray. So this is like more like real life, which is the inverse of what we do with ray tracing. So our light ray is going towards the camera, but it hits the lens not at the center. And that would be, and we don't have a real lens because usually a lens has multiple things, right? That help with making sure that the convergence happens. So, and then I guess we're gonna use. How are we going to wait? Is this enough to make things go out of focus? Really? Getting the origin wrong? Yes, it does. That makes sense. because what's happening is that basically it's like having confusion of what you're looking at. Like you're basically averaging with whatever is around it. In a way. Yes. We're doing the averaging stuff just like we did with anti-aliasing, but anti-aliasing happens at the destination. At the destination, we are sampling in the area of what we consider a pixel. Well, a section that then will become a pixel in our thing. But in this case, these extra noise that we're introducing, extra randomness, is not at the destination anymore. Now it's at the origin. And because it's at the origin, it has an effect that varies, that becomes greater with distance. Although it happens also in greater form, also getting close. Okay, so I don't have a perfect mental model of this, but I think I get a little bit of the basics. Okay, let's do this. So we now have a new way of doing vector origin. So you can get, array origin. So array origin, blah, blah, blah. So the origin for us was camera center. I'm gonna call this just origin, and I guess that's what we pass down here. And I'm gonna name this to direction. If the focus angle are greater than 0, then center, else back dot wait, this is the focus disk sample, so I think we need to implement this. What is center? Camera center. Okay, the focus disk sample needs to be implemented. Vec3 const vec.random unit disk. We need to accept random. And then we return camera center plus. Is this a add mul? This is an add mul, isn't it? So this is return add mul. Wait, is it add mul or mul add? Mul add. Mul add. Like 3. It's P times defocus disk V. No, fuck, it's U defocus disk V and 0 plus camera center, which needs to be splat. Oh, which we can do with an at in this case. Oops. Okay, let's see what we're doing wrong. Oh, what am I doing? There's no random in here? Really? Oh, I guess so far we have been doing random from objects. Rand state. No, it is in camera. Oh, we just never imported the interface. Okay. It's actually right below. God damn it. You know what? Then we can even avoid accepting since with these things this thing lives here. We can just do rand. There we go. Okay, so I think this works. Um, and so this is what we use up there. Okay, so we need to fix this call. There we go. We're building. So far, we don't seem to have anything going on because I think we don't have a big disk, do we? Which I think we express with this, which is currently set to 0. What if it's okay? Let's know. I don't know what the scale of these things is. 0.5. Maybe 0.5 is a gigantic number. I don't know. Wait, if it's 0, it builds. If this is 0.5, it doesn't build. Except the type F64. Found workers free. Oh. Oh. I guess we were just not calling this at all. So what was happening is that because we were resolving this at comp time, we were never going to call into this. And so that never caught our mistake. So here, I think what's happening is that random range gives you a random vector. So I think here's how we do it. This is not what the book does, and it's definitely less efficient, but we can do this. Just get one random vector, and then we do p at 2 equals 0. So we turn the third thing to 0. What? So this is not this? These are vectors. Oh yeah, that's true. These are vectors. So this gets splatted? Huh. Oh man, life is hard now. We don't see anything in focus. So 0.5 is a lot. 0.1 maybe. Okay, 0.1 you almost can't tell, but also the problem is that the focus plane is probably not centered around the spheres, so it's hard to like see change among them. And I by changing this number alone, this is not enough. We don't know what the distance is between us and the spheres. So you know what? Let's do this. Let's bump it up to 0.5. Okay, and let's do some experimentation. Like we basically need to figure out what the right number is. So this is at 10 meters. Let's see that the focus distance is 5 meters. I generally have no idea how far these spheres are. 5 meters seems to have made things better, I think. Let's say that the focus distance is 2 meters. Yeah, there we go. Now they seem to be perfectly in focus. Let's augment. Let's have more defocus. 1. Is 1 like a bad number? I think we are now seeing that a bit of everything is out of focus. What if we make this 1.5 or just 1? What if the focus angle was 10.0? What happens now? Then everything is out of focus. Does that mean that I'm not? I think I'm not nowhere near close these the right distance. Then 1.5. I think this might be even worse than 0.5. You know what? Let's see what the book suggests we do. Oh, there we go. The distance, so the correct distance is 3.4 and the focus angle is 10. Okay, 3.4. Let's go. Never mind. No, this is not working at all. The focus angle 10 and 3.4. With everything else being the same, nah. Although, wait a second. FOV of 20. We never got to FOV 20. Let's see. I think we have some bork math. We need to double check our math. We're doing something wrong because we don't see these. Okay, let's retrace our steps. I think this is entirely from here and downwards, right? There's nothing else before. So we might have borked something here. Here we're making a vector that has 3 components. The first 2 components are a random value between -1 and 1. And then we set P2 to 0. And then we do the magnitude. And if it's lower than 1, then we accept it. Magnitude squared. Well, we can do this. Wait, what am I doing? This was max is 1. The other one is -1 actually. So this would be +1. So this is 2 plus mean, which is -1. Yeah, I guess it's 64 plus 1. Does that make sense? So this is a value that goes from 0 to 1. In the range 0, 1. And we want to map this from -1 to +1. Is there anything better? We have float range, float exp, shuffle. limit range biased. Convert a random integer into an integer, blah, blah, blah. Int range, int range. There's no float range. Float norm. Return a float multi value normally distributed with a mean. Okay. Float exp shuffle. These are the only three floats we have. Okay, there's no float range. Because this would be 1 minus minus 1, that's 2. 2 plus minus 1 is 1, so it's this number times 1. But no, this does not work. Is this math wrong here? Multiplication takes precedence. Oh, you're right. Am I dumb? I'm dumb. Yeah, so you're right. So this would be then, so it's, we're saying this is 2. So this is the value times 2. That makes sense. The value times 2 minus 1. Yeah. There we go. Okay, and now this makes sense. Okay, so we have improved this a little, but I don't think this is going to make our image correct. I think we are borked. We have borked something else. Something else is wrong, I suspect. Yep, this should not look like this. Okay, what else we did? Defocus angle, focus distance, okay. Defocus disk Q, defocus disk V, yes. So viewport height. Okay, so viewport height is 2 times h times focus distance. 2 times h times focus distance. Then this stuff stays the same. Viewport U and V are these. Pixel delta is divided by width and height. Viewport U with viewport V height, yes. Viewport upper left. I think this is also correct because we are pointing at the right thing. I think we're messing something up afterwards. The focus radius is focus distance times. Let's see, the focus radius is focus distance times tan of degrees to radians of the focus angle divided by 2. Degrees to radians of the focus angle divided by 2. Yes. And then U times the focus radius. Yep. Gives us the 2 vectors. And then in ray origin, we say if the defocus angle is lower or equal than 0, then we say the center. Otherwise, we take a sample from the disk. And ray direction is pixel sample minus ray origin. Do we do that? Pixel sample. Oh, we forgot something. There we go. Now we got it. Let's have now a less insane FOV. So let's go back to 90. We're still centered. Perfect. And the focus is very strong. So let's push the focus distance back. So it's not 3.4. What if it's 4? So this should be focused then now on the metal sphere. And we are. Now the metal sphere is more in focus. And everything else is more. There's a ton of bokeh. Okay. We did it. So we got to chapter 14. Where's next? Let's see. Let's make the image on the cover of this book. Lots of random spheres. Oh no, we have 4 loops now? Oh no. Uh-oh. It's 4 loops time. Oh, some of them are glass, some of them are not. And and they're all sitting on a giant sphere. So this is what's funny. So far, we have only come up with how to solve like intersections for spheres. We haven't done anything else. We don't have other shapes. We only have spheres. So, yeah. Inline for bloat. Well, maybe this is a moment to move away from that to something else. Although, so far we're only putting in there spheres, so that thing might as well become an array of spheres. The spheres is the only thing that we have. Should we try to come up with something that isn't a sphere, maybe? Although I'm guessing that that's going to be the subject of the next ray tracing book, I'm guessing. Let's set up this scene. Let's set up the scene. Okay, let's see what he does. So there's a ground material, and then we make a sphere with ground material. That's going to be gigantic. Then we have a loop. Why do we start at -11 and then we go up to 11? I'm guessing because we're using these values also for positioning. Yeah, okay, then that's fair. Okay, so we're going to make choose mat random double. Wait, I'm not going to make the exact thing in the book then if it's randomized. I'll take it nevertheless. Okay. And then we have... Wait, then I'm confused. We have then 3 spheres. Oh, I'm guessing the big 3 spheres are positioned out of the loop. Okay, I'm going to copy all of this and then... and then implement it. So... yeah. Okay, so function, not in camera, but in main, go to end, and we do function world 1 underscore 1. It's a joke. World 1 1, and we return a slice of spheres. No, we return an array of spheres. I don't want to heap allocate. I could heap allocate actually, and it wouldn't be the end of the world. Yeah. Okay, so we start with some materials. So ground we had up here. Can it be computed at comp time? Absolutely, yes, totally. Yes. But I don't want to go bonkers with comp time if it's not really necessary. It's a little bit awkward to do it with comp time. But we could totally do it if we wanted to. Yeah. So ground material is an inversion. Albedo is 0 0.5, 0 0.5, 0 0.5. So this is it. And then we do this. Okay, so bar world. Camera render should be able to run a comp time, no? Yes, we'll be able to. So world is a SCD array list unmanaged. Empty. And then we do this, and then we do world.append GPA, and then also array list unmanaged of what? Array list managed of objects.sphere. Okay, append a sphere that has what's in a sphere. There's material, is ground, and then we have, I think, center 0 minus 1000 0, and then radius, which is 1000. Okay. Then we have this for loop. Okay, so I would do this for loop. So this is a for. Can we do minus 11? No, we can't go negative, can we? That is unfortunate. We need to use while loops. We could try to be clever with offsets. Maybe that's what we could do. We could go from 0 to, what is it, 22, and then subtract 11 to the number. Yeah. Random float. Also for random, here's what we can do. Let's call it rand. Check this out. Check this forbidden technique. I'm gonna make rand pub. um. Do. Okay. And then we say if center minus, oh my god, I don't know, I'm gonna call it P. Center minus like 3. 4, 0.2, 0 if p if vector magnitude of p is greater than 0.9, okay. Why are we making a material here? Why are we defining the material here? Then we set it and we give it to it. Set it, give it to it, set it. Why are we defining up here? I guess. Okay. We don't have to do this, I guess. So for us, it's just like a if. Random is not thread safe. How is it working? Oh, it's not thread safe? Then we're just using it wrong. That's what's happening. I guess we're not getting super high quality random. Are we using random in the threads? Yeah, we totally are, right? Because we're sampling stuff at random. Yeah, we would need to. Well, wait. Let me show you how we solve it. Watch me solve this in one stroke. Well, actually 2 strokes. Okay. There we go. So what were we saying? If choose material is lower than 0.8, color colon random. So this is a vector random times vector random. And then we do world.append. Also, we're missing tries. So world.append GPA. Conversion. It is albedo. Okay. So we did this. Then we have another if, well, else if. Zero 95 const albedo back dot random range const fuzz. Oh, god damn it. This is just a random number in a range between 0 and 0.5. So this is random float divided by 2. Okay, this one is easy. Why are we doing it like this? This is so weird. This is so weird because we're making all the spheres the same size. Is this sphere the same size? Man, this sphere is also the same size. So in reality, all we should be doing is just doing something different with the material, and then we then append whatever material we ended up with. That's what we append. So here's okay. Here's how we do it correctly. We put this at the end, and in here we do const material of type objects dot material is this, and here we have blocks. Well, actually, we don't even would need blocks. We can immediately do this. Sorry, what I'm doing doesn't look good because I don't have auto formatting right now because I have a bunch of C++ code placed in here. But it will all go back to normal in a moment. Just give me a second to actually get this stuff right. The electric, okay. Refractive index, I think it was. And this is a semicolon. Okay, I think. Oh, I lost the sphere initialization code. So let's put this here. Okay, you can go. Now, okay, now we need to make sure that our curlies are make sense. Well, let's try wall.append GPA center equals center, radius equals 0.2, and material equals material. There we go. Okay, so now all and then there's also this. Let's comment it out. Okay, we now need to make sure that we have parentheses that make sense, which is hard with how things are right now. Oh, there we go. We just need an extra one. Okay, let's see if this makes sense. So apparently we don't have vec3, so we'll have to get vec3. But setting it aside, here's how it works. We want to create one material. We switch on, we're not really switching, right? We're using if, but we're essentially switching on the condition. And then based on the condition, here we are creating a material Lambertian. Here we're creating a material matte. I forgot to restore the albedo computation. I think this was just a vec.random. And also fuzz. I think this was a random range. So this was rand.float of 64 divided by 2, I think. We can double check this in a moment. And then at the end, only once we append the sphere with the right material. Again, this does not look sexy, but yeah, that's kind of what we're actually trying to achieve. Okay, let's double check. Fuzz, yes, is random double between 0 and 0.5. Albedo is a random between 0.5 and 1. But it's a random vector. There we go. So random range. The one above, I believe, is correct. Yeah, it's random multiplied twice. The electric is just set to 1.5. So this is all good. And then there's 3 big spheres. Is this vec.vec3? We really don't have any vec. Oh, I guess I took it out. That's what happened. Okay, so these are all the things, all the for loops. Then 3 big spheres. Okay, big sphere 1. So try world.append slice GPA, and the slice is going to be the 3 spheres. So first sphere, second and third. So first sphere, center equals 0, 1, 0. Radius equals 1. Material equals dielectric dot refraction index equals 1.5. This is the first one. And you know what? I'm going to copy this instead of this. There we go. Second sphere is -4 and 1. So -4, 1, 0. Size is 1.0. Oh, they all have the same size, right? Yeah. And then the material is Lambertian. And this Lambertian has color 040201. Okay. Then the last one is 070605. Sorry, that's the color. Well, I guess we can do that. So the last one is metal. 765. Pass is 0. And the point is -410. No, what am I doing? It's 410. Okay. I think the run from SED Crypto is thread local. But I'm I don't know, could be, but that's not the one that I'm using. Let me just double check that I got everything right. I think I did everything now. So we add the final 3 spheres. I have 2 errors that we need to fix. So this is vec dot. And this is choose material. Okay, this is material. Why do you say that it's unused? Material. What did I write here? Material. Oh, we're outside the if. We do this only in the if, right? Yeah. Okay. In any case, so if we look at this here that we're using, default PRNG, actually, let's go here. Maybe random tells us. For thread local cryptographically secure pseudorandom generation, use SED crypto random. So you're right, but we're not using crypto random. We are fine with a crappier random in our case. And yeah, the crappier random is not thread safe by default, probably, or rather, well, we know this for sure actually because this is just a type. There is no instance of anything. We made the instance, so based on how we make it, like where we put it, we decide if this should be thread safe or not, and it wasn't, and now it is because it's a thread local. So okay, what's the next problem? Oh right, we need to wire this stuff back to the main function. So you know what, let's not do this. Let's cut. And this is like world 01. World 0. We're missing ground because we moved it over. It's kind of sad. Let's put it back. So ground, but it didn't have these numbers. But I guess it's fine. We're going to leave it there like this. So Okay. So down here, return world.items. Actually, let's try world 0 first. I'm curious if world 0 works without issue. Sorry. What am I doing? World 0 is the one without any GPA. It's all comp time creation. Let's see if that works. Unable to resolve comp time value. Right. No more inline. And now it actually can do the other flow control in there. Unable to resolve comp time value. Initializer of container level variable must be comp time known. Oh, that's kind of sad. I think Zig could figure that out. Maybe, maybe not. It's fine. So that means that we don't have rand in here. And then we need to create rand wherever it's necessary. Who else needs rand? So that means that also in main we don't have access to rand. Okay, there we go. Are we happy now? Uh, did we bork world 0? We might have borked world 0. What happened? So this is the funny part, right? Where you change something and now nothing works and you don't know what happened anymore. Uh-oh. Well, I guess we can change this to return 1, 2, 3, 4, 5. 5 spheres. And these are 5 spheres, so there's no confusion. It's 5 spheres. And we do this. Okay. So we're doing something wrong. We changed the color of the bottom sphere. I don't remember what was the original color, so we got something different. Okay, so now we can we can switch to word 1. Word 1, 1. I guess I'm just gonna call it word 1 at this point. Okay, let's go to word 1. Okay, now we have some problems. Incompatible use size and F64. Oh, nice. A and B also give us the opportunity of turning them into floats. Can you do this? You can't. Of course you can. You cannot. Float from int. Arguments found 0. Right, we need to pass rand. Next problem. No refractive index. Oh man, what's this thing called? Inversion, metal, refraction index. Refraction index. Refraction index. Okay, so I got it right sometimes, sometimes not. Parameter type declares here. What's the problem? Accepted type. Oh, we need to try. There we go. We're running and it's slower. It's suffering. I guess it's suffering because we have a ton of spheres. Oh, you know also what I forgot to do? I forgot to move the camera. We need to move the camera also. So this is going to be, well, we'll see what we get this time. But then to get the actual image that the book wants us to get, we are going to need also to move the camera and change the focus, like set all the parameters to the expected values. Suspense. Maybe we're going to be in the middle of a gigantic sphere and we're not going to see anything. Okay, so here's what's happening. We're trying to look at the scene, and I think there's one goddamn sphere right in front of our nose, blocking the view, completely out of focus, ruining the experience. You know what? I'm gonna save this. Move image ppm to noise ppm. Maybe this is gonna be my logo. Okay, let's see what are the camera stuff supposed to be. Samples per pixel. Oh, they do. Okay, so we're trying to get a high quality image, huh? Note that the code above differ. Yeah, note that the code above differs slightly from the project sample code. The samples per pixel is set to 500 above. For a high quality image that will take quite a while to render. The project source code uses a value of 10 in the interest of reasonable runtimes while developing and validating. Yeah, let's go ham, man. Let's go ham. Let's see what we can get away with. Camera. Image width. Yeah, 1980 is fine. 1980 is fine. 500 samples per pixel. How much do we recurse? Still 50. 4K so I can have a new wallpaper. Oh man, it's fine. Let's see how long it takes with these values. So FOV is still 20. Why do they like FOV 20? I don't get it. I'm thankful that I've never been in a Counter-Strike lobby with the author of this book because he would have made me go insane, I think. Then we have, so look from, it's 13 to 3. 13 to 3. But you know what? We need to have, you know what? We need to have something slightly personalized. I'm going to copy most things, but I don't want to do everything the same. Look at 0, 0, 0. I don't think I want to do this. And then what's V up? V up is perfectly up. And then the focus angle is 0.6. And then focus distance is 10 meters. Okay. So from above, what if we look at it from the other side? You know what? Let's do this with low resolution, so we can experiment a little bit and come up with our own personalized like approach to it, and then we decide. Okay, do we like this? This is kind of curious. Okay, what was 13 supposed to be? Let's see. Okay, so this is, I think, pretty much the scene that the book wants us to make. Let's double check that it matches. It doesn't really match, does it? Wait a second. What am I doing? Here, open. We are missing some spheres, are we? Aren't we? There's like, yeah, there's definitely way fewer spheres. And we don't see anything through this ball because there's nothing to invert, I think, behind. So I think we borked some of the math in here. I think the way that I rewrote, not in here, in main. I think that the way that I wrote the loop is maybe wrong. Let me think about it for a moment. We go from 0 to 22 and we subtract 11, which makes us go from 0 becomes minus 11 and 22 becomes 11. So, no, I think this math is right. I need to double check some other formulas. A plus 0.9 random double, 0.2 B plus 0.9 random double. Yeah. I think we might be borking this condition. You need to convert to double first, then subtract. Oh my god. You are right. Well, not necessarily, but you're right, because this is U size right now. But you're right, yeah. Damn, so dumb, huh? Must have a no result type. God damn it, dude. We're being hit by the non-result type stuff. That is so sad. Is it time for as? I think it's time for as. I avoided it up until now. I think it's time for it. It's time for it. Yeah, it's not in safe. Oh, you know what? Let's build in safe mode and let's watch it actually tell us. Really safe. Man, it even catches this while compiling. To be fair, even if it's released fast, we should still catch this stuff at comp time. I think it's a bug that release fast is not catching this. Oh no, never mind. This is a different thing. Wait, what am I doing? I'm dumb. Yeah, float from int. I'm dumb. I deleted too much code. Sorry. Okay, let's try again. There we go. We got failure. Panic integer overflow. Perfect. So it worked. Okay. This sucks. But oh wait, no more release safe, release fast. Okay, there we go. Now we have everything. Okay, so then for camera position, okay, what if we kept the original camera position? Oh god, let's do small size 400, 50 samples. Oh yeah. Okay, so this is the one, but it's more. It has more stuff in it. Okay, you know what? Let's make a high quality version of this one. So 1980, 500 samples. Let's go. Boy, is it struggling. We are now to a point where maybe even adding the second level of progress would start to make sense. It wouldn't really help make this faster, but it would make sense. Ooh, this is in pain, huh? Yeah, it's 920, 1080. Yep. Time to port to the GPU. Well, in the meantime, if I can use my mouse, uh, so for the next book, let's see, next steps. Let's see. An interesting thing you might note is the glass balls don't really have shadows, which makes them look like floating. This is not a bug. You don't see glass balls much in real life, where they also look a bit strange and indeed seem to float on cloudy days. A point on the big sphere under a glass ball still has lots of light hitting it because the sky is reordered rather than blocked. Okay. Let's see. Now you have a cool ray tracer. What's next? The second book in the series builds on the ray tracer you developed here. This includes new features such as motion blur, realistically rendered moving objects, bounding volume hierarchies, speeding up the rendering of complex scenes. Right now we're just trying to hit everything at the time, but you can probably have some kind of data structure that is able to encode the idea that, you know, if you have 3 spheres in a row and you have a ray that hits the sphere on the left because it's very on the left, and then it doesn't hit the sphere on the center, I think then you can say you can do some math to, you know, avoid, you can skip everything on the right of it, or roughly speaking, that kind of idea. That makes sense. Texture maps, placing images on objects, Perlin noise, random noise generator, very useful for many techniques. Quadrilaterals, something to render besides spheres, yeah. Also the foundation to implement disc, triangles, rings, or just about any other 2D primitive. Lights, how about a ComTime ray tracer? ComTime is low, by the way, chat. So it's already slow as is, running right now in release fast mode. You don't really want a ComTime ray tracer. You actually would prefer to make a release fast build of a normal ray tracer and run that in your build pipeline. Like, this is a point, by the way, this is a good piece of learning. To be clear, I understand, you know, the concept of, you know, let's do a wacky thing just for the sake of it. Totally fair. But I think it's an interesting point from the perspective of learning Zig. ComTime has use in specific circumstances, but you also have the build system. And in every situation where ComTime is not the appropriate tool, the build system is, generally speaking. So you should not think of Zig just in terms of ComTime. This is it's a view that is not, it's too restrictive. What you want is to think about build time, ComTime, runtime. You don't forget about build time. That is important. Okay, why is there that goddamn sphere right in front of this place where also, what, like, really, why is there a sphere up here? Should they all be on sitting on the giant bottom sphere? Yeah, clean your lens. In any case, I'm happy. This is gonna be my YouTube thumbnail, I think. So let me move that one. Okay. Let's make a real one. Also, you know what? I think we need like an orange. I think the ground should be more orange. What is the Zig orange? What shell are you using? I'm using fish. FOV 90 versus 20. I think I'm going to try to keep FOV 90. Well, no, but they want 20 for... Let's do their picture now. That was, what was it? 13. Or you know what? Let's do almost their picture. Okay, let me bump this down so we can do... Oh, by the way, you know how we can do this? We could have... Here's the cool way of doing this. What you do here is you do if built-in.mode equals .debug. You know what? Okay, you get the idea. I'm not going to do it because there's too many values that I would need to move around. But you get the idea. You can basically just toggle these ones based on build mode, so you don't have to fiddle with them like I'm doing every single time. So let's look at these numbers. 13 to 3. I'm going to do minus 13 just to see what happens. And then look at 0, 0, 0. Defocus angle 0.6. Focus distance there, the meter. Oh, also, you know what? We should try what I was doing before with a non-insane defocus angle. To be fair. Okay, let's see what happens. Yeah, so this is kind of the image from the book, except on the other side. Oh, 1980. Oh, God, sorry. Thank you. I didn't realize that that's what you were pointing out the first time. Where's this stuff? Oh, well, okay, I changed it. F7, A4, 1D. Shit, what's that in normal numbers? So this would be the big sphere, right? That would be ground. So let's see. 2, 4, 7. Thank you. 1, 6, 4. 29. Yeah. Okay. So this is good. In camera, let's do this. Let's do this. Oh no, what did we do wrong? Biggest coercion of division operands. Oh, I forgot the 0. Again? Oh yeah. Again. Yeah, that's much more colorful. Okay, let me try one thing. So I'm going to keep this, but here I'm going to go back to the original configuration. 1920. And the focus angle is going to be 0.6. Distance 10 meter. I don't know. Let's see what happens. I'm doing 50 samples per pixel instead of 500, so that's why it's more bearable. Okay, it still has the same problem of one sphere in front of the camera. It's so funny. But yeah, it works. Okay, let me make a high quality one. 500, and this is gonna be the one that I keep for the thumbnail for real. Okay, let's finish reading the book in the meantime. Okay, we're looking at Perlin noise, quadrilaterals, lights, add sources of light to your scene, transforms useful for placing and rotating objects, volumetric rendering, render smoke, clouds, and other gas use volumes. Ooh. Color is wrong probably because of gamma correction. Oh, sorry, I'm colorblind, so for me it's it's tough to know when it's right or not. I cannot take off gamma correction from only that, so we would need to pre-gamma correct it. I guess we can square it, right? The gamma correction was doing a square root, so if we square it, we should be countering that, right? Position -2 instead -2 instead of 13. Yes. I'm doing the weirdo image. I'm doing the one that has like one glass sphere right in front of the camera. Also, you know what? Right, if we are trying to get the color right, then I might as well stop this. Let's get the color right first. Okay, you know what? Training comma, multiple lines. Also, you know what? Let's also do this, and then we do. We have POV. No, we don't. Right? std.math.pov. Type f64. To okay. So let's see, book 3, Raytracing, the rest of your life. This book expands again on the content of the second book. A lot of this book is about improving both the rendered image quality and the render performance, focuses on generating the right rays and accumulating them appropriately. This book is for the reader seriously interested in writing professional level ray tracers and or interested in the foundation to implement advanced effects like subsurface scattering or nested dielectrics. Okay. I mean, I guess the problem of nested dielectrics is that you need to know both where you're coming from and what you're hitting. So this last one doesn't seem terrible. We don't have that, but it doesn't seem turbo hard. The rest, yeah, I don't know. Let's see, other directions. There are so many additional directions for you to take from here, including techniques we haven't yet covered in the series. This includes triangles. Most models are in triangle form. The model I/O is the worst, and almost everybody tries to get somebody else's code to do this. This also includes efficiently handling large meshes of triangles, which represent their own challenges. Parallelism. Run n copies of your code on n cores with different random seeds. Average the n runs. This averaging can also be done hierarchically, where n divided by 2 pairs can be averaged to get n divided by 4 images, and pairs of those can be averaged. That method of parallelism should extend well into the thousands, of course, with very little coding. Interesting. So they don't parallelize over like lines or kernels, but they parallelize on running the same algorithm with. If I'm understanding this correctly, the idea is that you don't put 500 samples per pixel, but you do 5, and then you run this same thing in parallel on a bunch of different cores, whatever, and then you average the images that you get to obtain the same effect as 500 samples per pixel. Let's see how we're doing. It would allow you to get real-time preview of the generated image. Yeah, I would also do that. I mean, this approach that we're doing also would allow us to get something, right? The problem is that we would get it line by line. By the way, this is another funny thing. Younger people in chat might not even know this, but there used to be a time where PNG files, depending on how you created them, would be nicer or worse to observe as they loaded. Like there used to be a time where internet was so slow that you would see images load line by line. There we go. I think this is the right orange, right? I think we got it right. We gamma corrected it right. And we got the same wacky image. This is it. This is my boy. Okay, this is the one that we keep. Okay. So success. Success. What can I say? We did it. So do I want to continue? I don't know. We'll see. That time was before PNG was a thing, right? I'm not sure. No. I don't think it was before PNG was a thing. I think that it actually is. I think PNGs can load in different ways. I might be wrong. There's a file format that you can define to load by line or by column, maybe even, or certainly in terms of like lower quality and then higher quality. It's JPEG that does that. Okay, then I was thinking of JPEG. Understood. Let's see. When I did this in Java, I made it with a live view, and then I did 1 ray per pixel looping on the outside. Yeah. So what you're describing is also right a technique that gives you the ability to preview things as they're happening in a way that like enhances quality. The parallelism that I'm doing right now would give you like line by line instead. In any case, okay. Yeah, we did it. Now do animation. What do you mean? It takes forever to do even a single frame. What's there to animate? Or do you mean like the animation of like rendering this thing? Yeah, I think I'm good for now, honestly. I'm happy with where I got. This seems cool. Oh, we need to read the last thing, right? Shadow rays. When firing rays at light sources, you can determine exactly how a particular point is shadowed. With these, you can render crisp or soft shadows, adding another degree of realism to your scenes. Yeah. Oh, when firing rays at light sources. Right. Have fun and please send me your cool images. Yeah, that sounds cool. To be honest, the one thing that I would be interested in, not right now, maybe in the future, is this part here. Or more generally, the idea of being able to load a model and ray trace that. For example, I believe that somebody a while ago made a 3D model of the Zig logo. I don't remember where it is. I don't know what file format is. I don't know anything about this stuff. But somebody made it. And so the idea is that we could load that Zig logo in a scene and ray trace it. In any case, very cool technique. Very cool ideas. I understood some of it, for sure. Not necessarily all of it, but I understood some of it, and it was nice. Oh, it's here? Oh, it's from Frank. Yeah, well, that makes sense. That makes sense. Yeah, but I'm not referring to Frank's version though. Although, I mean, if we have it, then for sure we could also use this. That would work. But somebody else made something else. This one that Frank made is designed to become a physical thing. The one that I saw was not a physical thing. Also, give me a sec. I have one. There you go. Check this out. I also have a Ziggy from Frank, 3D printed Ziggy, and I have another even cooler 3D printed Ziggy from Frank. Oh, you know what? Maybe I should do this. Pretty cool. Okay, so I'm happy. We did it. Yeah, was it resin printed? I'm sorry, I'm not an expert with regards to the materials, but I can tell you that it's pretty smooth. Smoother than other things that I've seen. Not perfectly so, but smoother. It's very nice. Yeah, I forgot. There's also a 3D Ziggy that was made. I think that Frank made the print, but I think that Frank did not make this model. Somebody else made this model, I believe. So here's what I think I'm going to do. I'm going to call it a day. This has been a good stream. So you know what? Let's give the goodbye to the people on YouTube for the purpose of the recording. So say hi, say goodbye to YouTube. And yeah, let's finish the video. Oh, here's what I will say though. To like kind of conclude this chapter, this book, this was a great resource. I enjoyed it a lot. I enjoyed complaining about C++, and I did make fun of the C++isms. I hope that the author, if they ever see this recording, which they shouldn't, but if they do, I hope they don't take it personally. Like everything, everything that we make is an artifact of our time. And I guess these C++isms in the past were more in vogue. Nowadays, not so much. But setting aside that, it was a very nice resource. I enjoyed it. It truly helped me get to the final destination. It succeeded. And I did understand something along the way. Not every single math formulas, not every single precise idea. Like if you ask me precisely how for example, autofocus stuff works, I'm not 100% there. But with some stuff I am. So it was definitely an awesome experience. So thank you to the author, and thank you for the people who have watched.